Everyone, so today we are going to discuss about quantum gates. Okay, we are having some quantum gates similar to logical gates in classical physics. So I have derived every mathematical representation with calculations in this particular video, so please listen carefully. So moving on to the first gate, that is nothing but identity gate. Okay, so identity gate, that the matrix representation of identity gate is nothing but I is equal to 1 0 and 0 1. Okay, these are nothing but the column vectors ket 0 and ket 1. The column vector of ket 0 is 1 0, whereas the column vector of ket 1 is 0 1. That you need to remember. So if you apply I on ket 0, that is nothing but I of ket 0, then you will be ended up getting, if you do the matrix multiplication, you will be ended up getting the result as 1 0. So that is nothing but 0 is already, we know, ket 0, but if you apply identity gate on ket 0, you will be ended up getting the same thing. This is nothing but ket 0 again. Okay, so there will be no change if you apply identity gate. So same way you try to do it for ket 1. So if you do it for ket 1, again the matrix multiplication. Okay, this is again matrix multiplication. If you see here, then you will be ended up knowing that identity gate does nothing on the basis. It looks like same as the above. Okay, so if you apply it with ket 0, then you will be ended up getting ket 0. If you apply identity gate with ket 1, you will be ended up getting ket 1. That is the thing you need to do. So I get does not modify the qubit. It is used for alignment and timing in circuits. That is the only use case of identity gates in quantum. Okay, now this is the important gate, Pauli-X gate. Okay, so Pauli-X gate flips the qubit. For example, if your qubit is 0, then it becomes 1. If the qubit is 1, then becomes 0. Same as above, this is the matrix representation of Pauli-X gate. So already we know ket 0 is nothing but 1 0, ket 1 is nothing but 0 1. So if we apply it on ket 0, same matrix multiplication again you will be considering here. So you will be ended up seeing some flip. So ket 0 if you apply, that is nothing but 1 0, you will be ended up getting ket 1 as the result. Okay, that is what Pauli-X gate do. Same way you do here also, same calculation again. So if you do the matrix multiplication again, so you will be ended up getting 1 0. Here if you apply it ket 0, you will be ended up getting ket 1. If you apply ket 1, you will be ended up getting ket 0. That is the working principle of Pauli-X gate. So Pauli-X gate flips the qubit state. So it is equivalent to classical NOT operation. Okay, that you need to remember. So moving on to Pauli-Y gate. So Pauli-Y gate is nothing but, this is how the matrix representation looks like of Pauli-Y gate. 0, minus I and I are nothing but the complex numbers. So or imaginary unit we call it as. Okay, so if please look the calculation. If you apply Y gate with ket 0, you will be ended up getting the same thing, that is nothing but I of ket 1. Okay, if you apply Y gate with ket 0, you will be getting I of ket 1. But whereas if you apply Y of ket 1, okay, you will be end up getting minus I. Here it is flipping but no minus, but here it is adding minus. This minus is, we call it as phase. Okay, what is that? Phase. So I think I mentioned here. Okay, this minus we call it as phase in quantum. Okay, so some phase change, okay, will be happening when you are applying Pauli-Y gate with ket 1. Okay, so now moving on to Pauli-Z gate. So the Pauli-Z gate keeps ket 0 same but flips the phase of ket 1. That is nothing but, if you apply Z of ket 0, you will be end up getting ket 0. But if you apply Z of ket 1, so you will be end up getting minus ket 1. That is the thing you need to remember. Okay, so that is what Pauli-X gate do. This Pauli-Z gate changes the phase of the qubit. It rotates 180 degrees. I will explain block sphere in one video. Okay, so block sphere is nothing but a 3D sphere where this gate rotates 180 degrees around z axis. Then it creates Pauli-Z gate. Okay, that is what the meaning of this particular sentence. Okay, so moving on to the main important gate, that is nothing but Hadamard gate. So here please look on to the definition. So the Hadamard gate is nothing but creates a superposition. What does it do? It creates a superposition. Earlier I think in the playlist I have posted the video how we are creating the superposition, that is nothing but 1 by root 2 ket 0 plus 1 by root 2 ket 1. So it transforms definite state, that is nothing but ket 0 and ket 1 into the mix of both. So this is how Hadamard gate matrix representation looks like. 1 by root 2 of 1 1 1 minus 1. So if you operate this Hadamard gate on ket 0 basis, you will be ended up getting 1 by root 2 1 1. So now how does this came? So you are thinking about how this result has been came from here. Here what I am doing is nothing but I am writing 1 1 as 1 0 and 1 1 as 0 1. So please look, if you add up those 1 plus 0 0 1 and 0 plus 1 1, you will be ended up getting this same result. So 1 0 is nothing but, as we know the quantum states, 1 0. So ket 0. 1 1 is nothing but, one more thing, this is nothing but ket 1. So this is how we are writing here. You need to remember this, how this shortcut. So the thing is, if you apply Hadamard gate with ket 1, you will be ended up getting minus, that is nothing but phase. Okay, that you need to remember. That is the small difference between Hadamard gate with ket 0 and Hadamard gate with ket 1. So if you go for phase gate, so this is nothing but we call it as phase gate. So what does it do is nothing but, if you observe it, it does nothing to ket 0. If you apply ket 0, you will be end up getting ket 0, no phase, nothing. But if you look on to this another second part, that is nothing but if you apply this on ket 1, you will be getting I, that is nothing but we call it as phase factor. Okay, so if it is rotated by 90 degrees on the block sphere, I will explain block sphere. Okay, so this is about S gate, and the one more gate is nothing but T gate. This is nothing but, here I missed one thing, pi by 8 gate, we call it as pi by 8 gate. Okay, so I think some error corrections are there, some minor corrections are there. So this is pi by 8. So the T gate is also called as pi by 8 gate, is like a softer version of S gate. It rotates the ket 1 state by only 45 degrees. Okay, it rotates that is nothing but it only rotates by 45 degrees, whereas S gate rotates 90 degrees. Okay, so what actually happening when you are applying it with ket 0, it will be ended up getting ket 0. If you apply it on 1, you will be ended up getting e power I pi by 4. Okay, this is, we call it as introducing small phase shift. This e power I pi by 4 is nothing but we call it as small phase shift to the gate. Okay, that is what we do. So until these what I covered, these are called as single qubit gates. Now I am moving on to that is nothing but CNOT, which we call it as multiple qubit gates. So we will be having a diagram, I forgot to mention that. So one is control, another one is target. Okay, this is how target looks like, and this is what control. So this dot and this is here one plus symbol will be there. Okay, this dot represents control and the plus symbol represents target. Okay, this is similar to classical XOR operation. So this is the matrix representation of CNOT. Okay, so this is based on tensor product. Let us say ket 0 is nothing but 1 0, and I have written combinedly ket 0 0, right? So this is nothing but tensor product. Okay, tensor product of again 1 0 1 0. Okay, so this is the tensor product. Okay, so 1 into 1 1 1 1, that is how you need to do. Okay, so you'll be ended up getting this result, tensor product, and you will be ended up getting this result. This is how this matrix has been written. Okay, and next we are moving on to some operations on CNOT. If you operate 0 0, that is nothing but it is multiple qubit gate. So if you operate ket 0 0 on CNOT, you will be ended up getting ket 0 0. There is no change in output, you will be ended up getting the same output. Okay, so what does this say is nothing but when control is 0, target won't change. Okay, here if you see control is 0, so this is control. Okay, target won't change. So that is the thing you need to learn from here. Okay, let us talk. Here control is 1. Now please look into the operation. So if control is 1, so target is 0 right here. So you will be end up getting 1 because control is 1, target changes. Control remains same but target flips. So if for example in this case you are having 0, for example let us think we are having 1, so you will be end up getting 0. So what happens? So here you will be getting 1 1 right. For example I am having 1 1 as my base state and I am applying CNOT on this. Okay, so my control is 1 and my target is 1 as of now. If you apply CNOT, you will be end up getting what is the result? 1 0, because control is 1, target flips. So but in this scenario you are having control as 1 and target as 0, that is why you are ended up getting 1 here. Okay, that you need to remember. Okay, next one more gate, this is also important gate, that is nothing but control Z gate. Okay, so it is just like CNOT but it has a twist. Instead of flipping, it adds negative sign. Okay, only if both qubits are 1 1. Okay, so in this particular scenario it won't add minus. Okay, in this particular scenario no minus because they are not 1 1. In this particular scenario no 1 1. Okay, but in this particular scenario what does this control Z gate do is nothing but if the qubits, 2 qubits are 1 1, then if you apply control Z gate you will be ended up getting minus ket 1. Okay, minus ket 1 1. So that is what the meaning of control Z. Okay, so this is how, so I have given the calculation here. So this is how you looks like. So meaning, so the output gains negative phase, meaning a 180 degree shift. Okay, this you need to write in your exam, this makes boost in for your answers. Okay, so this is what, so 0 0 because 0 0 does nothing because it is not 1 1. 0 1 it is not 1 1, so does nothing. 1 0 it is not 1 1, does nothing. If it is 1 1, so control Z only adds minus if it is 1 1. Okay, that is what control Z operation is. Okay, so now moving on to one more gate, that is nothing but swap gate. Okay, okay, what happens here is nothing but it is literally swaps 2 qubits. For example, if you are having a qubit 1 0, okay, so it just swap it. Okay, if you swap them you will be ended up getting 0 1. What is that? 0 1. Okay, so this is what we do using swap gate. Okay, this is the matrix representation of swap gate. So if you operate, I have operated this 1 0 on swap gate and I am ended up getting the result of 0 1. So the 2 qubits have exchanged their position. That is what you need to remember. Okay, so if it is 0 0, so there is same element, there will be no swap, you will be ended up getting the same answer. If it is 0 1, let us say, then you will be ended up getting 1 0. If it is 1 0 0 1, okay, If it is 1 1, so there two are same, right? So the basis remains same, that is nothing but get 1 1, right? So some are there. So exchange 2 qubit states, useful for rearranging qubits order in quantum circuits. This you need to remember and write in your exam for better understanding. So moving on to the last gate of our this particular session. So this is nothing but Toffoli gate. This is the matrix representation of Toffoli gate. Okay, Toffoli gate is represented as CNOT, that is nothing but controlled NOT gate. Okay, but whereas in CNOT you will be having one control and one target, right? So one control and one target, but whereas here we'll be having two controls and one target. What are those? Two controls and one target. So how does we are operating here is nothing but, if first two controls, for example, I am having one example, so I haven't given the matrix calculations because it is very large. So if two controls are 1, so then only target flips. If two controls are 1, then target flips. What is the target here? The last element is the target, so target will be flipping, so you'll be ended up getting 1 1 1. So if these two are not 1 1 or 1 0, for example, in one other scenario 0 1 or 1 0 0 0, then target won't change if you apply CNOT. Okay, that is what you need to know. Okay, is that, I hope everyone is clear. If any doubts, let me know in the comment section. So thank you guys.